All right, let's take a look at section 12.2, which is going to cover vectors. So learning objectives this time around, distinguish between a vector and a point. Also, we're going to go ahead and add a scalar to that as well. So also the difference between a vector and a scalar. I'll want to think about vectors both mathematically and graphically. And then we're going to define the characteristics of a vector and then calculate it. So defining and calculating the length of a vector, and see what it means for two vectors to be equal. So let's start off with the simplest part. What is a vector? So a vector is a quantity that has both a magnitude and a direction. And if we pick 2 points and we call them A and B, then the displacement vector AB is going to be the directed line segment that moves from point A to point B. So the vector will matter which letter comes first. Since we write the vector AB, that means going from A to B versus BA would be going from B back to A. I'll also define that starting point as the initial point. So A, in this case, is the initial point, and B is the terminal point, or where it ends. And we're going to say that two vectors are equal as long as they have the same magnitude and direction. So first off, let's just say that when we're saying magnitude, this really just means length. We can kind of use those two terms interchangeably when we're talking about vectors. The magnitude of a vector or the length of a vector means the same thing. And also we said that two vectors are equal as long as they have the same magnitude and direction. So it doesn't necessarily mean they start and end at the same point. As we see from figure 1, we have two vectors. One is AB, the other is CD. AB versus CD. And those are equal vectors because they move the same distance and they have the same direction. Sometimes it will be useful for us to call vectors by a single letter instead of just naming their starting point and their ending point. So for example, these two vectors are also labeled V and U. Now when it comes to the textbook, whenever text wants to talk about a vector, it's going to use a bold letter V to mean the vector V. But in the case of just writing in these notes, since it's rather difficult to write in bold, if I want to talk about a vector V, I'm just going to put a hat on the letter V. Let's maybe do that in a color that's not blue. So V with a little hat means the vector V. All right, then the length of a vector, which again is just the same as the magnitude, we'll define that, or we'll denote it by either a series of vertical lines on either side, similar to an absolute value sign, or a series of double lines. Again, those two notations will be used interchangeably. And then we're going to define what a magnitude looks like for both a 2D vector and a 3D vector. So if we have a vector that goes between a pair of 2D points, A and B, then the magnitude of that vector is just the distance between points A and B. We saw that distance formula in the last section. Same with, we're going to go into 3 space. The magnitude of that vector is just the distance between those 2 points, just this time in 3 space. So X, Y, and Z. Then let's also talk about a position vector. Since vectors have the same length and direction are equal, it's oftentimes easiest to find an equal vector that starts at the origin, and then just claim that our vector is maybe easiest described as starting from the origin rather than going between 2 points A and B. So we look over to the right and see figure 13, 2 representations of the same vector. But we're going to have the position vector being the one that goes from the origin to a point P. So that is the definition. The position vector of P has the origin as its initial point and P is its terminal point. And if we have the point A1, A2, A3, then we will write the vector A1, A2, A3, but with pointy brackets. So for emphasis, if we have A1, A2, A3 with parentheses versus A1, A2, A3, but with pointy brackets. The pointy brackets mean that we're talking about a vector, whereas parentheses mean we're talking about a point. So a point, like we're used to seeing, has parentheses, and a vector has these pointy brackets. So if we're listing out its components, a vector will show up with pointy brackets. Should also define what we mean by components now. And so the components of a vector, if we're working in some mathematical space, the components would be each of A1, A2, and A3. So a vector can have an X component, a Y component, and the Z component if we're in 3 space. And so here we have another representation of a vector taken straight from the text. Let's take a look at an example. We'll leave that definition up at the top of the screen. On the following cases, find a position vector, v, such that v is equal to ab. So I'll want my vector v to be equal to the pointy brackets of, if I want to go from a to b, then I should take the b value and subtract the a value. So let's maybe highlight a couple of these. How about magenta for B, yellow for A? So we're going to look at -1 minus 1 for the X component, and then 0 minus 2 for the Y component, and get a vector that looks like -2, -2. And then into 3 space, if we're going to look for yet another vector, we can look at B and we'll look at A. Then our vector V could be the vector -1 minus 2, and the X component, we'll look at 2 minus 1 in the Y component. And finally, -3 minus 0 on the Z component. Giving us the vector -3, 1, -3. Then, if you'd like to see the graphs of these vectors, you should be able to go and check the class notes available on D2L, which will link to the document where all of these notes are being taken. And I'll be sometimes adding extra updates that show up just in the notes and not necessarily in the video. So these graphs should be there in the class notes. All right, and then as an example, we'll look at a generic length for a position vector. So if we wanted the magnitude of A, that should be, since this is a position vector, it means that we're starting at the origin and then going to the point A1, A2, which means we're going from 0, 0 to A1, A2. And so we should see that this magnitude is equal to A1 minus 0 squared plus A2 minus 0, again squared, giving us the square root of A1 squared plus A2 squared. And then if we did the same thing, but for a 3D position vector, we're going from the point 0, 0, 0 to the point A1, A2, A3. And I think it can be seen rather clearly that this should just be A1 squared plus a2 squared plus a3 squared, since we'll just be subtracting 0 from each of those a components and then squaring them. So we'll go 0, 0, 0 to the point a1, a2, a3. And again, note the use of parentheses instead of pointy brackets when we're talking about a point versus a vector. So the other term I want to define in terms of vectors is a scalar. And so a scalar is going to be just a number in the way that we've already been thinking about numbers up until this course, where it's just a number, whereas a vector will have both a magnitude and a direction. So just a number could be considered a magnitude. So the main difference between a scalar and a vector is that a vector is going to have some sort of a direction associated with it. In terms of notation, the text, we said if the text is talking about a vector, it will just have a bold letter for vector. And again, I'll be using a little hat for when I'm writing out a vector, since again, it's hard to write in bold, but a scalar is just a regular old letter. So if we use a to represent a scalar, it's just a. And if we use a to represent a vector, it's a with a little hat on top. And then just as an example of a scalar and a scalar is just the number 7, whereas a vector in 3 space might be something like 8, 5, 3, where it has each of those components, an x component, y component, and a z component. Okay. So if we then want to talk about what vector addition looks like, we'll just take 2 vectors, in this case u and v, and just line them up tip to tip to get their sum. So if my vectors u and v are the 2 in blue, then u plus v would mean first taking the vector u and moving to the end of it, and then starting from the end of u, adding on the vector v, and then going in its direction for its length, getting us the total single vector u plus v is just after I traverse along u and then along v, u plus v is where I would end up. We can see then from figure 4, if we looked at v plus u instead of u plus v, I mean first going in the direction of v and then in the direction of u, and we end up at the same point either way. So v plus u or u plus v doesn't matter for vectors. We can add in either order. And then if we want to look at the difference between a couple of vectors, so take u minus v, that just means we'll go forward in the u direction, but then backward in the v direction. So we can see that v kind of moves towards the upper left. So negative v moves toward the lower right. It's in the exact opposite direction of v. And u minus v is just the vector that I would get if I started at the origin, then traversed along u, and then backwards along v. All right, and then scalar multiplication. So again, we said a scalar is just a number. So I could multiply it into a vector. And if I do multiply a scalar into a vector, that just means I'm going to multiply each component of the vector by that scalar. So whatever that number is, just multiply it into each component. So that multiple is the absolute value of c, or the magnitude of c, times the length of v. And the direction is the same as v if c is positive, but it's the opposite direction of our vector v if c is negative. And then if c is 0, or if v is 0, then the multiplication, or the scalar multiplication of c times v will come out to 0. So it doesn't matter if our scalar or our vector is 0, they both come to 0. Note the fact over here that 0 is in bold, which means that we are talking about the vector 0. 0, 0, 0. If we're in 3 space, it would just be 2 zeros if we're in 2 space. And then figures 7, 9, and 10 just show a few examples of some scalar multiplications of vectors. So if I take 2v, that's just a vector in the direction of v that's twice as long, whereas 1/2 v is a direct vector in the direction of v that's half as long. Negative v has the same length but goes in the opposite direction. Negative 1.5 v, opposite direction, and 1.5 times the length. All right. Then a couple boxes full of just properties of vectors. I'll leave these here for you to look over on your own, but they hold up pretty similar to just some regular addition and subtraction rules. All right, then let's define a unit vector. We say that we say a vector A is a unit vector if the magnitude of A is 1. So that'll be important if we're just looking to get a vector that goes only in a specific direction, but we're uninterested in its magnitude. Oftentimes it is helpful to divide away a magnitude from a vector, leaving just a unit vector. So it'll still point in the direction that we want to go in, but it will have a magnitude of 1 associated with it. Oftentimes having a magnitude of 1 makes it really nice if I want to come up with a magnitude of a specific, or a vector of a specific magnitude and in a direction. We'll also define the standard basis vectors, and those are the unit vectors that go in each of the x, y, and z directions. So 1, 0, 0 is I, 0, 1, 0 is j, and 0, 0, 1 is k. So each of those are vectors that we'll use as direction vectors, so that if we know the x, y, and z components, or the x, y, and z magnitudes of a vector, we can just multiply those by I, j, and k, and then have our direction and our magnitude be somewhat separate. But so again, standard basis vectors are I, j, and k. Now let's put all that together in an example. So we're going to take the vector 6, negative 2, 3, and our first step is going to be to find the unit vector that goes in the direction of A. So that unit vector should have the following. It should just be the vector A divided by the magnitude of A. Note that when we get the magnitude, that's going to come out to a scalar value, meaning it's just a number. So if we take the magnitude of A, we should get the square root of 6 squared plus negative 2 squared plus 3 squared, which is the square root of 36 plus 4 plus 9, which I believe comes out to the square root of 49, meaning that that magnitude is just 7. So our vector A has a length of 7, and if we want the unit vector in the direction of A, unit vector should be equal to 1 over 7 times the vector 6, negative 2, 3. And it's oftentimes probably just easiest to leave the vector written out this way, particularly if our magnitude isn't going to simplify once it multiplies in. But I could also multiply that 1/7 into the vector itself. So 6 over 7, negative 2 over 7, and 3 over 7. So a vector of magnitude 1 that points in the direction of A. Then number 2, I'll want to find a vector of length 42 that's in the opposite direction of A. So if we wanted to do that, we want a magnitude of 42 or length of 42 and to go in the opposite direction of A. So I'm going to take negative 42 and multiply it into the unit vector. So A over magnitude A, which looks like negative 42. Oh, so to kind of explain where all that's coming from, we know we want a length of 42. So I'm multiplying the 42 into the unit vector, which already has a magnitude of only 1. So magnitude of 1 times the magnitude of 42 will be a magnitude of 42. And I want to go in the opposite direction of A, so I'm multiplying by a negative. So negative 42 times 1/7 times the vector 6, negative 2, 3. Notice I'm using the first orientation just because the math will work out a little bit simpler. 42 over 7 is 6. So we should get the vector negative 36, positive 12, and negative 18. So there we have a vector that has a length of 42 and points in the opposite direction of A. And finally, we'll write the vector in terms of the basis vectors I, j, and k. So the vector A is equal to 6, negative 2, 3 in the standard vector form we've been using, or if we separate it out into its I, j, and k components, this is 6i plus, or not plus, this will end up being minus 2j plus 3k. Again, I, j, and k are those standard basis vectors mentioned earlier. So just break up those components, put it on each I, j, and k. And then one more example dealing with components. A golf ball is hit at an angle of elevation of 30 degrees at a speed of 15 feet per second. Find the horizontal and vertical components of the velocity vector. So we just break this down for a moment. This 30 degrees would be a direction. And when we're talking about speed, that's a magnitude. The speed is just a number. It says how long the vector should be. And that 30 degrees, that angle is telling us what direction it should go in. So if we break this thing down, bring out our ruler, set it to 30 degrees. There we go. And then draw that component, or draw that vector. We should get this velocity. It has a length of 15. So we want to break it down to its horizontal and vertical components, which means breaking it down into a vertical component, which could be this piece, and its horizontal component, which can be this line. Let's change that to be a slightly different color since I'm using yellow and purple. And we create a right triangle where we know we have an angle of 30 degrees right over here. 30 degrees. So if we want to break this thing down into its horizontal and its vertical components, maybe I'll label those X and Y, and they are just the legs of a right triangle, where X, the horizontal component, is the adjacent side of that triangle, and the adjacent side should be equal to the hypotenuse times cosine of theta. So 15 times the cosine of 30 degrees. And if you recall back to trigonometry, the cosine of 30 degrees is the square root of 3 over 2. So this is 15 root 3 over 2. Then the y component, which is the opposite side, if we wanted to relate sine and an angle and the hypotenuse together, or the opposite side, the hypotenuse and an angle together, then we'd have that the sine of 30 degrees is equal to opposite over hypotenuse. So that opposite side y should be equal to the hypotenuse times 15. Or let's try that again. The hypotenuse times the sine of theta. So 15 times the sine of 30 degrees. There we go. And if you recall, again, from trigonometry or the unit circle, the sine of 30 degrees is 1/2. So this should be 15 over 2, meaning if we wanted to rewrite that velocity vector, it is equal to the horizontal component, 15 root 3 over 2, and the y component, or the vertical component, 15 over 2, or breaking that down into its basis vectors, 15 root 3 over 2i plus I plus 15 over 2j. There we have it.